This is Lab 2 for Physics 2, distributing the amount of charge on a U-tape evenly across the length of the tape. The purpose of this lab is to develop a computational model that represents the tape as a uniformly charged line by distributing the total charge evenly along its length rather than approximating the charge as concentrated at a single point. Although the experimental approximations estimated the excess charge on one U-tape to be 2.33 times 10 to the negative 8th coulombs, the computational model results suggest that the magnitude of the charge on one piece of tape is actually 2.22 times 10 to the negative 8th coulombs. So approximately 2 weeks ago, we completed an in-person experiment, Lab 1, where I estimated the excess charge on clear tape by bringing two equally charged U-tapes together and measuring the distance at which one began to float. And then we assumed that the tapes had equal charge, behaved as point charges, and that forces were balanced between electric repulsion and gravity, and then we used Coulomb's law to calculate the charge. The tape was found to have a positive excess charge of approximately 2.33 times 10 to the negative 8th coulombs, and this lab demonstrated that electric charge can be estimated using simple experiments and reasonable assumptions. For this week's lab, we have a few key new physics notes to discuss. So the first thing that I think is important to discuss is charge as a whole, which we refer to with the variable Q. And charge is an intrinsic property of subatomic particles that gives rise to the phenomenon of experiencing force in the presence of electric and magnetic fields. And so, in essence, these fields exert influence on charged particles, resulting in observable effects. We also have a new principle called the field of a line of charges, and it's important that we look at the superposition principle, which states that the net electric field / force is the vector sum of contributions from all charges. If you remember from our initial lab, we assumed that the tapes were each point charges. However, that's slightly inaccurate because the tapes are actually behaving with multiple interactions, such as that seen in the picture shown below. In this lab, we used initial conditions in our coding. So for starters, the system is the top tape, the surroundings are the bottom tape, and Earth. Initial conditions, we had to declare some physical constants, such as K and the gravitational constant near Earth's surface. We also had to declare the mass of one tape, and then we also used the estimated net charge on one tape that we found in lab number 1. Also, I think it's important in the initial conditions to talk about how we defined the electric field, and we used the formula for the electrical field of a point charge. The first question we had to ask ourselves in this lab was, what assumptions, approximations, or idealizations did you have to make to determine approximately the amount of charge on the floating tape? Well, we modeled each tape as many small point charges that were interacting via Coulomb's law. And Coulomb's law can be seen in this image shown to the right, the electric force is equal to the K constant times the charge of the particle 1 times the charge of the particle it's interacting with over the distance between them squared. We also ignored external effects such as air resistance. Additionally, we assume that each tape carries the same total charge and that charge is uniformly distributed along the length of the tape, and this can be seen in our code. So the code models each tape as a uniformly charged line using the line charge function, which divides the total charge Q into equal pieces and creates evenly spaced charge elements along the tape. Additional details of the coding: the electric field at each charge on the top tape is computed with the E-field function, and a nested loop sums the contributions from every charge element on the bottom tape, applying the principle of superposition. The force on each top element is then calculated using the formula F equals the charge times the electric field, and these forces are accumulated into F underscore E underscore on underscore top to obtain the total electric force. Finally, the magnitude of this net electric force is compared to the gravitational force, and arrows are displayed to visualize both forces. If you can see here, however, the magnitude of the electrical force differs from the magnitude of the gravitational force. So, similarities and differences between our coding, our computational model, and our actual lab we completed. Well, the assumed charge value does not produce equilibrium for the given tape mass and separation in the computational model. Error from this could be excess handling of the tape, leading to loss of charge. We also used an estimated charge in the computational model. And then also non-uniform charge distribution in reality. We assumed there was a uniform charge distribution, but this is really not the case. And then what was the magnitude of the charge of one piece of tape as calculated by your computational model? So to do this, we had to multiply that external electric field times the charge. I solved for Q in this case, which was the charge, and I used the electrical field of a rod since this most closely resembled our tape. And I found it to be 2.22 times 10 to the negative 8th coulombs. So discussions. So for starters, what if we had modeled that tape as a single point charge instead of that line model charge. Well, that's what we had done in the first lab, and we found actually that point charge model resulted in an overestimate. And why do these estimates differ, and which one's more likely to be closer to the real value? Well, in the point charge model, we are assuming that there exists only one field. However, in the line charge model, we are assuming instances of multiple fields. And the tapes are more likely to have multiple interactions as seen in the diagram above, so the line charge model, which considers a distributed charge across the tape, likely results in a more accurate estimate.